Thanks for inviting me. Thanks for having me. And yeah, I'm with LYRO Robotics, and I'm going to do a bit of a different spiel here in terms of like what we're trying to do at LYRO Robotics, but also a lot of the stuff that we do at LYRO actually comes from the Australian Centre for Robotic Vision, and we've published some of that at ACRA. I have an ACRA 2016 shirt on, by the way. So I'm trying to give a bit of an overview of what we do at LYRO, but also how the research that we've done has actually helped us to get to a point where it is actually commercially viable to build robotic systems. So what is LYRO? LYRO is a robotics startup that spun out of the Australian Centre for Robotic Vision. I'm the managing director and co-founder of LYRO, and we're just based here in Brisbane, south of Brisbane, 8 Mile Plains. And what we're really looking after is trying to build robotic systems that are smart enough to pick and pack quite literally anything that you throw in front of them. And more specifically, we want to have 100,000 robots out that can do this by the end of the decade. So why do we care about 100,000 robots? Well, there's a very large challenge going on right now, and it's been even emphasis through the whole ongoing global situation. But how do we build secure, safe, and reliable supply chains? That's not a simple task. And specifically here in Australia, especially if you look at agriculture as one of the sort of leading industries there, you have a high number of transient labor force, more than 50% in some cases. And you have a lot of these positions unfilled. Actually, right now, there was an EY study that came out just a couple of weeks ago. There's 26,000 jobs unfilled. Right? So that's 26,000. That's not just 26. And there was other studies that basically say more than 50,000 part-time visa holders have not entered the country recently. So there's a very, very large number of people that are currently not here to do jobs, specifically in the supply chains that we're actually relying on. Same thing with online sales, 17% year-on-year growth, and that was before this year. This year, you actually see this step function in February, March, when all of a sudden everybody started ordering online. And so we need to solve these big problems. And robotics has, historically always claimed to solve big problems, but now we need to do it. And we need lots of robots to do it. We don't just need one robot or 3 robots out there that help us do things. We need 100,000 robots out there. And we've seen more and more people getting into that. Advanced robotics, which is sort of a catch-all term for everything that has to do with a bit more modern robotic system, whether you want to call them Industry 4.0 or machine learning or intelligent systems, has seen a 21% growth. And especially given with the pandemic going on, we've seen an incredible surge of interest for no-contact packing. Some of the outbreaks globally actually have happened in food processing plants, which is not particularly good. So how can we help with robotic systems? So I guess for me, the big point here is, what's the difference between deploying one robotic system and 1,000 robotic systems? I hope there's some students still on the line and young researchers. I think that the really crucial difference from trying to get into industry, unless you want to do a consultant's business, is you need to really be able to scale up your operations. You need to think about problems in terms of hundreds and thousands of robots instead of one. Building one robotic system is relatively easy, right? I mean, we all in this together. We all have built robotic systems. You take a bunch of hardware, a bunch of software and sensors and stick them together, and it works. And it's good enough to get maybe a research paper published at ACRA or ICRA or wherever it is. But how do we actually translate this into an impact for a larger scale? And one thing to think about is, what is actually the product that you're trying to sell? It's not the technology that you're selling. It's not the robotic system that you're selling. What is the product? And we at LYRO basically looked back at what is it that we can do. And we developed and deployed the world's first fresh produce pattern packing robotic system. That's a bit of a mouthful, but what that actually allows you to do is quite literally any vegetable, any fruit, we can pick up with our robotic system. We can place it in any pattern, whether that's how you find it at Woolies or any other supermarket, or if you need to put it into a shipping container. And we can do that at any time. How we built that? We're building that based on what we call LYRO machine intelligence. But the critical part here is not the LYRO machine intelligence. The critical part is like how to build these robotic systems that can actually have this broad applicability. Because I think that's the only way that we can solve these large-scale problems out there. LYRO machine intelligence is sort of similar to the terminology that was used by William in his framework and by Jeff in the UFR autonomy. It's sort of the catch-all term for more the outwards-facing customer side of things. As roboticists, it would be called machine learning, computer vision, robotic grasping, whether that is hardware and software parts, and we bring them all together. For the outwards-facing worlds, that's the brain, the eyes, and the hands. And that's really sort of our modular stack that we allow to stick together and quite literally makes any robotic system smart enough to pick up a lot of items. You can see some on the bottom there. There's a few videos here as well. Over the last couple of months, so as LYRO, we are a pretty young company. Over the last couple of months, we spent a lot of time trying to robustify the underlying technologies, the underlying research that came out of the center to actually allow us to work in different industries. So on the top, you can see e-commerce on the left and agriculture on the right. Work on different robotic systems. Very similar, again, on the top, you have a Kinova arm from a Canadian company. On the bottom, that's LYRO Generation 2 robotic system that does e-commerce fulfilling. And we trialed these things out in the commercial settings as well, right? You have to get out of the lab and do these things. And so this has really been a bit of a focus for LYRO for the last couple of months. And so how does that actually tie in with the technology that we've developed at the Center for Robotic Vision, and how does that tie in with like transferring that into an application area? So historically, I've been with the Australian Center for Robotic Vision, a long-term research initiative. Most people at ACRA probably know us from robots.c shirts that we wear when we go to conferences. I was based at QUT, and that really sort of like has been the next step of the journey for me to build robotic systems. I've started doing that during my PhD, and I like the Jeff's comment on getting smaller and smaller robotic system. My 2000-ish master thesis was on swarm robotics, and the whole idea there was, can we build smaller, more agile robotic systems to get them out there. But over the last couple of years, it was really focused on, can we get an understanding of the world from computer vision? And at LYRO, we are basically taking this, and as I said before, trying to put this into a product where, yes, the robot needs to understand the world, and yes, the robot needs to pick the world, but for a customer point of view, the robot just needs to work. And that's really what we're trying to do. For LYRO, we sort of started with a lot of the solutions and technologies that came out of our Amazon Robotics Challenge win. It's a robotic system that we built in-house, so tech stacks that we've developed at the center over lots of years, partly accidental, to make lots of different students work with different robotic systems. But it's a highly modular and functional design where we have lots of different AI and vision stacks that work together, multiple camera systems if needed, multiple gripper systems if needed, and really sort of bring them together into one nice sort of package. And for us, the Amazon Challenge, both challenges that we entered, was really, from an academic point of view, more a showcase and a student project than actually a research project, right? So it's a lot of engineering and education, but not necessarily research. But that was really the foundation that allowed us to say, well, there's actually an impact that we can have with these technologies in the outside world. There's an impact that we can have beyond what is just your fundamental research agenda. And we can actually take this out and have an impact on a broader scale. So what part of technologies are actually in there? And I guess that's sort of maybe one of the interesting things for the academics and as I said, the early career researchers out there. When you're in academia, you don't tend to think about the whole system as your research agenda. You think about different parts. And in grasping, my background is in grasping, it comes about picking, moving, and packing. So these are really sort of the more fundamental actions or blocks, if you will, that we need to stick together to actually build a system. And a lot of these things were developed at the Australian Center for Robotic Vision, or even a long time ago with sort of the iCub that I did during my PhD, more like probably a decade ago by now, on like doing this reactive reaching and grasping, where we actually used a very similar leap motion sensor that William showed. So it's good to see that from academic research that sort of translated into industry. But really the focus there was on small scale issues, right? So how do I synthesize a grasp point? Lots of research work goes into that. How do I do vision in loop grasping? And we have papers, both with ACRA and ICRAS and so forth, that specifically focus on these parts. And all these things are very crucial and very important. But from a research point of view, you look at them in sort of separate parts or in sort of isolated silos, because that actually allows you to compare your results, you benchmark your results, and publish your results. But as I mentioned before, the APC and the ARC were really sort of at the first move where we started to bring these things together. And really the research focus for LYRO is on bringing these things together. So it's really more focused on I guess sort of the slight gray in the bottom there that sort of brings these things together and goes more towards packing, which is sort of the application, and away from each initial parts of that. So a lot of time was spent on how do I take research code, or any sort of open source code, whatever the latest craze is in computer vision, we take and see, well, can I use this? Can I modularize this? Can I put this on a robotic system? And what are the benefits for the application area? So a lot of time was spent on building these sort of fundamental systems. At the second point is also like building a lot of processes and capabilities. So in computer software and sort of software managing and I guess the whole sort of IT sector, you see a lot of Devops applications now popping up, and that's short for development on operations. And the idea there is that you're not just developing in isolation, but actually you feed back the information from your deployments, from your operations back into your software stack. And we at LYRO basically have a very similar approach to our hardware systems. To get 100,000 robots out there that actually work, we have to get a few robots out there to see where they actually have a benefit, where they help out, where they have an impact, and take that back into our development. And we call it DVDP, which is development and then deploy. And so this is something that really has happened over the last 12 months and was a significant effort, which sounds in a way separate and different to sort of your research, if you come from academia research agenda, but it really is actually just a natural extension, or some people say the second side of the coin that sort of allows you to do product development that comes out of all this research that has been done in academia. And so in our specific setting, we've developed multiple instances of our physical instances of our hardware that we can actually test and deploy. Whether the deployment is in our facilities in a dark room where we can actually change lighting condition and change other aspects of it, or actually going to an industry partner. But these are critical and crucial for us to understand where we can improve and where we need to improve our systems, whether that is, as I said, on the brain, the eyes, and the hands, whether it's on the vision side of thing, the machine learning side of thing, or on the hardware side of thing. And if you don't deploy, you will not learn these informations, right? So as I mentioned briefly before, we are sort of at the third iteration, the third generation of our robotic systems. So basically every couple of months, there's a new iteration. We also use other robotic systems like UR arm, Kinova arm. We've looked at Frank arms and Cook arms to actually test whether that development cycle has an impact on the operation, not just in one application area and one robotic system, but on multiple robotic systems. And for me, again, the critical point here is we need to have a look at what can we do at scale. Fundamental research is very crucial and very important. And people that talk to me know that, but I'm definitely very interested in fundamental research. But now, as sort of a startup industry person, the important part is how do you turn this fundamental research into application area? And for me, that's the exciting thing. It's sort of a different approach to it, but it is very important to understand from day one, what is the scale that you want to do? It is a very different problem to think about 100,000 robots by 2030 than it is to think about like this one robot deployment with this one company in 6 weeks' time, right? And it's very similar if you think in terms of PhD student mindset, writing one paper, with you cram, you push for it, you might take some shortcuts, or you find the right results that you support your hypotheses. But if you want to have like an ongoing long-term success, you actually need to bring all these things together. You can't be too scattered to do your research. And it's very similar with the robotic systems here. Like, what is actually an important aspect to save in the long run costs and understand what the benefits for our customers is very critical. And obviously that is something where there's a trade-off, right? Like, each individual customer has maybe, as William said before, maybe 10% of your code needs to change to that specific or morph into that specific application. But fundamentally, what needs to work for 100,000 robots? And why, again, 100,000 robots? This does sound maybe a bit ridiculous, and Sue Key might have some good stats on how many robots we actually currently have in Australia, and it's by far not 100,000. But we have 26,000 unfilled positions just in agriculture. That does not include manufacturing, does not include e-commerce, does not include waste management. And this is really a critical problem for us right now. So, in short, how do we get there? We're working on it. It's a long road. What we want to have is these 100,000 robots out there. In other terms, that's like 50 million grasps an hour, if you want to have other large numbers. We want to deal with a wide range of objects, from just 0.01 kilo to 3 kilos is just a range. We're really focusing on things where we can have a large impact right now. And obviously you want to pack these things into different sets of boxes that are everywhere, from your Amazon boxes here on the left to stock standard boxes, which turns out the standard varies significantly globally. So there's a lot of challenges in there. And a lot of these things we can solve by bringing in fundamental research. But for a company, for us as a startup, we need to look at how to bring them together in a smart way so we can actually build reliable solutions. Thanks for that. I'm Juxi. You can reach me with these email contacts. I'm also going to be on Slack if you have some specific challenges. This is the team of LYRO. Thanks for having me, and shoot with your questions now.
Live, okay. Juxi, thank you so much. Very, very cool stuff. Congratulations on success of LYRO. Regarding that, I have a question. It's actually my own question. Do you think that your success in the Amazon Picking Challenge has played a role in the existence and creation of LYRO? Or if you had just done well, but not being at the top like you were, LYRO would exist? What are your thoughts on that? Just a sort of a non-technical question here. So
no, a very good question. I think LYRO would not exist without the Amazon Robotics Challenge. For me personally, I think it was one of those moments where it clicked and I realized that all these technologies, they're cool by themselves, but we actually have a way to stick them together, and we can have an impact outside of academia, and we can have an impact in society and economic with that solution. So for me, that was a click. That click would have probably also happened if we were not number one, but probably access to media and capital does help if you're winning a global competition. So that would have probably been a longer and harder road to raise our initial funding. But this is, I guess, two sides to it. But I think it's fundamental for me because it sort of allowed me to stick things together and see that they actually work.
Okay, thank you. Another question, could you comment on the precision versus reliability for in-field manipulation?
Thanks, that's a great question.
That's from Tirta, yeah.
Yeah. Look, the answer is it depends. A lot of people ask us, what's the speed, what's the accuracy, what's your precision, what's the repeatability? But actually, nobody cares. Like even the people that ask in industry, they don't care. What they do care is how many boxes get packed per hour, how many items get packed per hour. And we have people that come to us and say, oh, I want to buy this $2 million robot and put your stack on it. And it's like, sure, we can do that. But why do you need a $2 million robot? And they say, well, because it's the fastest and most precise. And then you actually look at what you want to deploy that, and it doesn't fit the problem, right? So I think a lot of questions come from people looking at numbers and assuming that higher is better or lower is better, depending if your accuracy or speed. But I strongly believe that a lot of people are misguided on that. And it's even more so if you think about in-field, like actually going into the field manipulation, like in the paddock. I think industrial robotic systems are not the right way to go forward there, because there's so much variability and uncertainty that precision on repeatability tasks is not necessarily the right argument.
Okay. And another question from Ressa. In your field, do you think that industry and R&D are far at the moment in terms of robotics? How far do you think these two things are, industry and R&D?
Let me rephrase that. Like the R&D in terms of like academic research, I think we are significantly further ahead than what industry research is doing. And that's because the last decade has seen a lot of breakthroughs in AI and computer vision modules that are driven by GPUs. Industry R&D, I think, is starting to pick up, but it's by far not where academic research is. I think there's a lot of gaps that can be translated from academic research into industry research. And I think for me, the critical aspect is I think industry research should be focusing on the aspects that I mentioned before, like the reliability aspect and the integration aspect, and take the things from academic research that like are specific subparts or sub-solutions that can be translated into that. Otherwise, I think there's going to be a lot of repeatability and the same research being done into like academic fields and industry fields, which might not push us forward as a whole field.